Hi, my name is now Murata, and I'm a student at UAH. And my project over the summer was electron temperature and density measurements of an arc plasma using optical emission spectroscopy. So I'd like to answer one question first. Why is this study important? So my project is preliminary experiment of fusion propulsion system. So why do we study fusion propulsion? Currently, manned space exploration is focused on beyond the Earth and Moon system, and it is necessary to invent efficient propulsion system in order to take the travel time shorter. And what is the benefit of shorter travel time is astronaut doesn't have to be exposed to radiation for a long time, and also it is good for the mental and physical health of astronauts. So we think fusion propulsion will meet our needs because it has extremely high specific impulse compared to the chemical propulsion. A typical chemical rocket engine has a specific impulse of about 450 seconds. However, fusion rocket has a specific impulse of about 130,000 seconds. This is high efficiency. And previously, a preliminary study for fusion propulsion system was conducted using low temperature plasma jet in order to ascertain the feasibility of plasma deflection due to the Lorentz force. And in this experiment, we used cold plasma, and characteristic of the cold plasma is electron temperature is much higher than heavy particle temperature. However, for the fusion propulsion, the electron temperature and temperature of a heavy particle are almost the same. So that's why we use arc plasma in our project over the summer, because arc plasma has similar characteristic to the fusion propulsion system, which is electron temperature and heavy particle temperatures are almost the same. And also, electron density of arc plasma is higher than cold plasma. So that's why we thought arc plasma was good test bed for the scaling towards fusion propulsion system. Also, arc plasma was necessary for the future experiments such as Thomson scattering. So how do we get the arc plasma? Arc plasma is formed between the two electrodes in the vacuum chamber. And we apply the high voltage onto one electrode, and another electrode is grounded. So this exceeding voltage results in the electric breakdown between the electrode. So the air between the electrode became conductive, so the current goes through from the one electrode to another electrode. In this process, the gas produces plasma and emit the visible light. And this is a video from the lab experiment. We can see the bright light. This is the arc plasma. So this is a setup for our experiment. This is the vacuum chamber, and inside the vacuum chamber, we placed two electrodes, and we apply the voltage from the power supply onto one electrode, and we use the power supply which has maximum voltage of 1200 volts, and another electrode is grounded, as you can see on the picture. We apply the gas into the vacuum chamber. In this experiment, we use argon due to its lower ionization energy. And we use lens to collect the light from the plasma into optical fiber and we use spectrometer to get the data of intensity of the wavelength. And this is the electrode holder in the vacuum chamber. One of the struggles in our experiment was finding the material that has high temperature resistance. Since arc plasma has high temperature, and all the material we are using in the RE experiment were either melt or burned. So we decided to use the tungsten electrode, which has high resistance to the temperature. And also we used the glass tube to protect the brick from the temperature from the arc plasma. So this slide is about optical emission spectroscopy, OES. We use OES to obtain the intensity of the spectral lines of the light. And we could define the composition of the gases that emit light by analyzing the data, since each gas has unique spectral emission lines. So this is example data from OES we got. And when we see it, we can tell this is the argon spectra. For example, around 750 nanometer wavelength, we see the high intensity, and 810 nanometers, we can see the high intensity. So each gas atom has high intensity at the different wavelength. So that's how we know this is argon. So intensity values and its wavelength were used for the electron temperature and density calculation. This is the experiment condition. And we use 5 different sets, and we took measurement about 10 times for each set so that we can take average, so that we can get the high accuracy result. So I changed the condition slightly between each set. For example, the difference between set 1 and set 2 is the plasma color. Set 2 is white plasma and set 1 is purple. Similarly, set 4 and set 3's difference is plasma color. And difference between set 1 and set 3 is the current. Set 1 is 304 milliampere and set 3 is 510 milliampere. And difference between set 4 and 5 is the pressure and flow rate. So the reason why we changed the condition is because we wanted to know how the current, flow rate, pressure, and plasma color affect on the electron density and electron temperature. So this is the plasma color. Left side of the picture is the purple plasma, and right side of the plasma is white color. It is a little bit difficult to see the difference of the color, but a big difference is white plasma is more bright, and purple one is more steady and less bright. And we assume that the reason why the plasma color is different is because of the different atom that is ionizing in the plasma. So next, I am going to talk about the method we use to calculate the temperature and density of the electron in plasma. First, I'd like to talk about corona model for temperature measurement. The diagram on the left side is important to understand the corona model. Argon atom has 2 excited level, which is 2p and 1s. And 2p has 10 different states. 2p1 to 2p10, and 1s level has 4 states, which is 1s2 to 1s5. When the argon atom transits from 2p state to 1s state, it emits certain wavelength of the photon. For example, when the argon atom of 2p1 state transit to 1s2 state, it emits the photon of 750.39 nanometers of wavelength. This slide is also about the corona model. This equation on the top is the important equation for the corona model, which is the intensity of the spontaneous emission from the transition. All the parameters are known. For intensity, which is I, and lambda, which is wavelength, we can get these values from OES. An example of the OES data is on the right side of the diagram. And we use this equation to make the intensity ratio equation. So as I explained in the previous slide, each transition of the atom emits a certain wavelength, and certain wavelength has a unique intensity. So for example, 2p3 state to 1s4 transition has unique wavelength, and 2p1 state to 1s2 state emit the certain wavelength of the photon. So we plug in the number and values from the OES data and all the parameters. In this equation, only unknown in this equation is K, which is rate coefficient. And rate coefficient is the function of the electron temperature. So when we plug in all the values we know, the only unknown is going to be the electron temperature. So that's how we get the temperature of the electron from this equation. And second method we use is to get the temperature of the electron is Boltzmann plot method. This is the main equation for the Boltzmann plot method. And so we make the scatter plot with MATLAB, and y-axis is going to be natural log of intensity times wavelength over G is statistical weight times A, which is transition probability. And x-axis is the energy of the upper level in EV. So we plug in the intensity and wavelength value from the OES data. And in this project, we use these 6 different wavelengths we used. We make the scatter plot and use the linear fit, because the temperature of the electron is going to be 1/over slope of the linear fit. And the important assumption for the Boltzmann plot method is local thermodynamic equilibrium. Under this condition, the excitation temperature and electron temperature and heavy particle temperatures are the same. And for density measurement, we use SAHA-Boltzmann equation. This is very simple. And we know all the parameters in this equation. Intensity and its wavelength can be obtained from the OES technique. And also the electron temperature, we use the data from the Boltzmann plot method. And next is about the result. So this is the result from corona model. We used a wavelength of 826 nanometer and 794 nanometer. And second column is the temperature we got from the corona model. And the temperature we got from the corona model was lower than we expected. We were expecting that arc plasma's electron temperature is going to be about 1 eV to 10 eV. However, we got about 0.3 to 0.4 eV. And we think the reason of this big error is high pressure. We use 2.28 torr and 1.715 torr. However, corona model is varied with low pressure, lower than 0.0075 torr. And under this condition, other collisional processes are not significant, which result in less effect on the excitation of the excited species. So we use extremely high pressure compared to this condition. So that's why we got the lower temperature than we expected. However, we analyze this data, we see one characteristic, which is white plasma has higher temperature than purple plasma. When we see set 1 and set 2, set 2 has higher temperature than set 1, and set 2 is white plasma. Similarly, set 4 has higher temperature than set 3, and set 4 is white plasma, and set 3 is purple plasma. So this is one thing we can tell from this result. And next result is from Boltzmann plot method. Left plot is from the OES data, which is argon-1 spectral line intensity versus wavelength. And right side of the scatter plot and linear fit is from the Boltzmann plot method of set 6. So we use this slope to get the temperature of the electron. So this is a result. Similar to corona model, we see that white plasma has higher temperature than purple plasma. When you look at the set 2 and set 1, set 2 has higher temperature than set 1. Similarly, set 4 has higher temperature than set 3. However, we couldn't define how the current affect on the electron temperature in plasma. When we compare set 3 and set 1, set 3 has higher current. However, set 3 has higher temperature. However, when we compare set 4 and set 2, set 4 has lower temperature even though set 4 has higher current than set 2. So that's why we couldn't define how the current affect on the electron temperature in this project. Also, we couldn't define how the pressure affect on electron temperature. In this result from Boltzmann plot method, set 4, which has high pressure, has higher temperature than set 5. However, in the corona model, the result was opposite. Set 5 has higher temperature than set 4. And next, this is the table of the result from SAHA-Boltzmann equation. And SAHA-Boltzmann equation is for the density calculation. And density of this plasma is 3rd column to 6th column in this table. And we use different wavelength pair and compare if the data is consistent. And over the same set of data, the density is consistent. And also similar to the temperature, higher density, white plasma has higher density than purple plasma. Then we compare set 2 and set 1. Set 2 has higher density than set 1. And when we compare set 4 and set 3, we see set 4 has higher density than set 3. Next slide, we compare the density and temperature, how these two affect each other. And from this plot, we can see that as the electron temperature goes higher, the electron density also goes higher. So in conclusion, the result of the electron temperature is about 0.675 eV to 0.845 eV. And electron density was 1.4 times 10 to the 21 meter cubed to 6 times 10 to the 23 meter cubed. And when the plasma was white, it has higher electron temperature and electron density. And in this experiment, corona model was invaried because of the high pressure we used. And the dependency of the pressure, gas flow rate, and current was not determined due to the short range of these parameters. So testing over a wider range of pressure, current limit, and flow rate is going to be useful for the future study. And lastly, I'd like to say thank you to the mentor, Dr. Xu, and all the grad students at the lab who supported my project. And this work was supported by the National Space Foundation CPU to AL program. Thank you so much.
Hi, my name is Flasmy, and thank you for watching this video. Make sure to follow us on our social media at CPU2AL on Facebook, LinkedIn, and Instagram. Bye!